Hey folks, welcome to a tutorial that's going to go over how to take something like Niagara Grid 2D and render this sort of system using locations. It can handle quite a few locations at a time, and the other really nice benefit is changing the size doesn't really affect performance too much. It also does come with the added benefit of controlling what exactly you're sending. So in my case, my alpha channel is the density info, and then I have also RGB, which is pretty much all of the color info from the nodes as well. So when I have something like this playing a mix on all of these nodes, you can see it's following the entire mix, and I'm using this color information to apply onto the fog map as well. So we won't be going over this exact setup, but what we will go over is something like setting up the density, because the color is really just another additive on top of that. So this is what we'll be setting up today in this tutorial. So we have a render target, and all of these sphere locations are applying to the render target, and you can even see there's this blended fade effect as well that is transitioning and interpolating over time based on where these positions are. So what we'll do is we'll start from scratch pretty much. I'll go over these two blueprints that are in the example project, and then we'll create all of this from scratch. What we'll do first is we'll just take a look through at what exists already, because it's important to understand kind of the data that we're going to be sending to Niagara. We don't have to set it up because you can just go ahead and download this to start with and follow along. In begin play, I'm caching the original location of the actor's component. Then from here, I'm randomly changing the size of the sphere, and then using this random size to create a radius value. So you can take a radius value here, and we can apply that later to the information we're sending to Niagara. Then at the bottom, this is just for animations. So we have a random play rate on this timeline. And this timeline is a simple sine wave that is bobbing up and down, and we'll apply it to the cache location, adding 100 in all the axes except for Z. We're multiplying by Z a little bit more just to make it go up and down a little bit more. So that gives us this back and forth motion that kind of allows us to have a nice little test bed for all this stuff. But the main thing is the location manager. So this is where in begin play, we're grabbing all of these actors and we're putting them into an array. And then from this array, we're grabbing the length of the array and we're setting the size of this location in sizes. And what this is going to be is our actual vector 4 array that we're sending to Niagara. So on event tick, we have all of our location actors. We're looping over the array and then setting this location and size value per actor based on the actor location. And then the radius is being pumped into the W value of the vector 4. So this is the data that is being sent over to Niagara. When we actually have an emitter, we'll come back and we'll fill this in, and then the material as well. So this will be the user variable that we're sending, and we send the data through. So when I hit play and they're moving around, if I hit F8, I can click on the plane and take a look at the location and sizes here. And this is all the data that we are dealing with. All the data is there and ready to go, and all the different radius sizes are the last value. Okay, so to start things off, we're going to go ahead and make a render target. We right click, go to textures, and then we can go to render target, and we'll call this RT underscore mix grid 2D, and then locations. And then from here, we'll double click to open it up. The default size of 256 is fine. We'll change the address X to clamp and the address Y to clamp. That just tells the texture to not wrap over and over and over again. It's just going to be clamped at the edges. And that should be good enough to start with. Then from here, we are going to make a material, and we'll call this underscore mix grid 2D underscore locations. And this will be the simplest material we'll ever make. We can go to the shading model, change it to unlit. And then for the texture, we'll type texture sample in here. And then find our RT underscore mixed grid locations as default. And then we'll plug the RGB value into emissive. So now that we have a material, we have a render target, we can make our system. So we'll right click and we'll make a Niagara system. And we'll create an empty system by default. And then we'll call this NS for Niagara system underscore mixed grid 2D underscore locations. And then we'll double click to open it up. By default, this will be completely empty, but we'll go ahead and right click and do add emitter and then empty. This is different from doing right click, add empty emitter, because it comes with the emitter state and the initialized particle, which is what we want right now to make the emitter actually work. We'll click on it and we'll hit F2 to rename it. We'll call this grid 2D example. And then from here, we will delete the sprite render because we won't need it. And then click on properties at the top and go to sim target, change it to GPU, and then also change the bounds to fixed. And this is just a more efficient rendering method. And then as far as getting the data into it, we'll go ahead and add these user variables. So we'll do a user exposed at the left here, hit the plus and do vector4 array. This will be our locations and sizes. It's very important that you call it locations and sizes. From here, we also have the texture render target as well. And we'll call this texture render target. Now we can go ahead and back out real quick and go to the mixed grid 2D location manager. And the reason why I'm having you set this up is just so you understand how this stuff is hooked up. So we have this set vector4 array. This is setting on this Niagara system grid 2D locations. If we go over here and we click this, this is an empty system at the moment, and we'll fill it in with the one we just made. And you'll notice when we fill it in, these user parameters will actually fill up, and the texture render target is set to none. So we need to go ahead and click this and make sure we set it to the render target that we created. And what this will do now is it'll actually write directly to that render target and just verify that locations and sizes matches up with this user.locations and sizes. Cool, so now that this is set up, we can go over to the render target plane, and then we'll set the material on here to our mm_grid 2D locations. And that pretty much sets us up for everything. So if you hit play now, you'll still see nothing's gonna happen yet, but we can actually start making things happen. The first thing we'll also need to make sure is that under plugins, we have our fluids plugin activated. And this is actually needed in order to just set the resolution of a grid 2D. It's just something in the module moved to the fluids plugin for some reason. So just that's a very big gotcha with UE5 is they moved it to the fluid. Now inside of here, we can add our grid 2D. So underneath our emitter attributes, we'll go ahead and we'll type in grid 2D collection. And we can just type in grid and grid 2D collection will show up. And we'll make a grid 2D collection. We'll call it the grid. And then we'll also need a render target. So then from here, we'll just type in render and you'll see render target 2D. And we'll call this render target. So kind of from a very basic perspective, a grid 2D is literally just cells in a grid that you can store data into and manipulate over time. And the reason why it's important to do this over something like the particles is that you can actually tell Niagara to loop through a grid cells instead of the particles update. So we're going to use simulation stages in order to do that. So to start things off, we'll go ahead and we'll click and drag into the spawn to set our grid value. And then from here, we'll also click and drag the render target as well. And this will just do an initialize on the grid. And then the really important one too is we have to hit plus on a new module, turn off the library and type in set. And then this will give us a grid 2D set resolution. And this is how we set our actual size for the grid 2D. So we have our grid. This sets up the data format, and it's really important that in here you toggle on and off the override buffer format. This is just kind of like a bug in Niagara that you need to get past. So I've just been going in and just setting this to half float anyway, so it kind of gets past the bug. But that if you don't do that, you're going to have issues initially setting data on your grid. Next, we have the render target. So on the render target, we'll set this to 256 by 256. And then I highly recommend to not use inherit user parameter settings. Just keep it with the values that you come in here because this checkbox has the tendency to crash if there's no data. And then at the bottom here, we're going to link our render target, our user input that we made and actually set the render target to the data interface. So our render target that we made now outside of Niagara, this guy, the render target mixed grid 2D locations, is now linked to the data interface that is going to store all the pixel information from that render target in order for us to manipulate it. And then the last thing we'll do is we'll set the grid here. So on this grid 2D set resolution, we have to click and drag the grid over. And then we'll set these cells to match our render target. So if you wanted like a 512 or 1024, you wanted a bigger render target, you could do that. Just make sure to set your cells and your render targets to the same for this example. Now that we have that, we can set up our stages. All simulation stages really are doing is they're changing how the particle system updates. So by default, if you add particles in a particle update, this means that it's going to update and iterate, and this module stack will apply per particle. What we're doing is we're changing that. We're saying, now we want you to actually do it per grid instead, per cell in the grid. And the way to do that is to go to plus generic simulation stage like I just did. Then if we click on none, we can change none here, change the name of it to right to grid. And then the iteration source here, we will change to the data interface. And then underneath data interface, we'll connect our grid. And that's just basically telling it to switch this specific stack here to iterate over the grid 2D cells. We'll go ahead and we'll add another simulation stage. We'll call this one right to texture. Then we have our iteration source. Again, we'll change the data interface, except this time we'll change our iteration source to the render target. We want to iterate over the render target's pixels instead of the grid 2D cells. Then the last thing we'll do is we'll also add a final stage, and this one will move up, so that way it's above right to grid and right to texture. And we'll call this one Initialize. Initialize. There we go. So the entire goal of this stage is to just set the grid's data to something by default that isn't white. And this is just a way for us to prevent a bug where it'll start white and then like fade to black. Cool. So this is our basic simulation stages, and we can go ahead and just set up a very simple setup here to just get a color to right to every single pixel. And then from there, we'll expand. So here under right to grid, we'll go ahead and hit plus. We'll type in new scratch pad module. This will give us a module to start working with. And it's very important to kind of understand where this goes. So you have your parameters here, your user parameters, which is all the inputs into the system, and then your local modules. And then underneath local modules, you can go ahead and change this scratch module to whatever you want. So right here now, I'll change this to right to grid. And then from here, we can go back and you'll see that right to grid's here. And then we have the module right to grid. We'll do the same thing for right to texture. So we'll do new scratch pad module. We'll call this one right to texture. And now underneath the right to texture, we have the ability to do some stuff. We'll go back first though, actually to right to grid. We will set up a color. So here we'll just go to set linear color. We'll call this RGBA. And then we'll right click, because you'll see it makes a local variable by default. We'll right click and we'll change the namespace over to stack context. Stack context is automatically writing this data into the grid 2D data interface. So if you go back to our system, the context is essentially like this stack, and then the data interface is linked here. So it's automatically saying, okay, when we're iterating over the cells of the data interface, we can use this to set the data on the data interface for us. So it's kind of a very magical namespace in that sense. So in this case, we'll go ahead and we'll set this to like a blue color, and we'll go over to the right to texture now, and we'll now write this blue color to the texture. So the way that we're going to do this is we'll take in an input of the grid. So we'll get the grid 2D collection. We'll call this grid, and then we'll hit plus again, and we'll do render target 2D. And then we'll say render target. And then we'll use this grid here. And we'll sample the grid vector 4 value. We'll also click and drag off of this, and we'll type in exec, and you'll see there's an execution index to unit. This essentially converts the current index of the cell to whatever unit of the grid data. And then we'll use the attribute name. The attribute name needs to be RGBA. It needs to match up with whatever you name the stack context value to be. And this value here will write directly to this render target. So we'll go ahead and we'll say set on the render target, and we'll set the render target value. So this will give us the ability to set per pixel based on the cell information of the grid data. So what this gives us is if we plug this into here, we then need one more thing. So from here, we can go ahead and say grid, and then we'll say execution again. And then we'll say execution index to grid index, and this will give us the index X and index Y of the grid here. So this is how you set it up in order to set the render target value. And now we've pretty much done everything that's in Partikel's tutorial video. If we did everything right, we should actually see something change. I believe we also need to go into this right to texture. Yeah, we need to make sure that the grid is actually hooked up to the inputs. So type in grid on the input here, and then we'll type in render target here. And now if we go back to our world, you can see right away, we already have a blue color showing up on our render target, but we can go ahead and hit play and make sure that when we change these values here, that it'll change to different colors. So if I change this to purple, this changes to purple. Change it to red, reddish orange, this changes to orange. So using this, we can expand upon it now and do what we need to do for each one of these spheres using the data that we have. So before I even go any further, I'll set this back to black. Boop. So now that we have the basics of setting a color on our render target, we can go in and start doing this a little bit more intentional. What we have is all these positions, right? So every single one of these positions is in the data. So we have the positions of our spheres. What we're going to do is we're going to loop through the cells of our grid data. So if you kind of imagine that these are the individual cells of our grid data. Cool. And then we have the radius of each of these spheres. So if I kind of make a circle here, we can see that each one of these spheres has their own radius. And then basically what we're going to do is we're going to say, okay, get the distance of the sphere. And then we'll say if we're inside, if this pixel is inside of the distance of the sphere, we're going to render it white. If it's not, we're going to render it black. Now this essentially gives us something like this, where we get these circles that are all going to be white, and especially if you can't color in the lines like I can. Okay, that's the very basic premise of what we're going to do here. And the only way for us to really do that is to jump into a little bit more advanced like HLSL code. So we'll start off and we'll get the data we need inside of this write to grid. So we'll go back to our Niagara system, and then we'll go to our write to grid module. So in here, this is where we were setting the color. So we can move this over and give us some room, and we can take the grid data 2D collection, have that as an input. From here, I think this is the only thing we need at the moment, and we'll grab the execution into grid index from the grid, and then we will also grab the num cells. So we'll get num cells. So execution index will go from 0 to 256 per the cell, and then the num cells will always be 256. And what we're going to do is we're going to take these num cells, we're going to multiply them by a negative 0.5, both the x and the y value, and then we're going to add them to each of the x and y values. So both of these will add together. So then we can drag off of this and do make vector. So we say make vector. And inside of make vector, we'll connect our x and y values. We'll leave z as 0 because we don't need to do anything with z at the moment. And then we'll multiply the n value here by a float. And then take this, click and drag it over to the plus for an input. And then we'll rename the input. You can hit F2 to rename it to world scale. And this just gives us a way to scale up and down the positions in order to align it properly to the size of the plane in the world. And then we'll take this output value and we'll set it to something called grid location. So this is simply just taking the grid information, the cell data that we have. Based on the position that we're at in the current cell, we can convert this data over to a centered world space value. So we can actually use this value right away just to illustrate what it's even doing. Or actually, we'll just go ahead here and we'll say get, and we'll say the location. And then we'll break this vector, and we'll put the X value into the RGBA. And you'll see it'll just convert it. All the channels will go into RGBA. So now if I hit apply, what we should get is this value going into our RGBA. However, I always forget this part every time. Every time I do anything new, I always forget that you have to go back to the system overview, and then you have to hook in the data that you need. So the grid 2D here will be this, and then our world scale will set the 1. And you'll see right away, we have our data being set to our centered positions. And the reason why this side is black is because these numbers are negative and these numbers are positive. So now if we go back to the write to grid, we just prove that our grid location has data, which is really good because it's good to prove kind of throughout the stages of doing something that the data is actually there and what you expect. The other thing that we need is the vector 4 array. So we'll hit plus on this, hit vector 4 array, and this will be our locations and sizes. Then we also have a float input that is going to be our radius scale. We're going to have to write our own HLSL. And the reason why is because this location and sizes is an array, and we need to iterate across the array per cell. So we can go ahead and we can click and drag off of this, and we'll type in HLSL. And now we get this custom HLSL. And it's really important when you're clicking and dragging these to add inputs that you rename the inputs to something that is different. These names have to be unique, or else you're gonna run into some really weird bugs that make your head explode. So if you right click on the inputs and you go to name, what I like to do is just kind of add the prefix of in to all the values. And now we have our InGridLocation, in locations and sizes, and then in radius scale. We'll go ahead and hit Control A and delete all the data in here. And then we'll just prove that the HLSL works similarly by clicking and drag off the output pin. Now, same thing here, you have to rename this to out RGB. And then what we'll do is we'll say out RGBA equals InGridLocation.x, and then we'll put a semicolon at the end. And what this should give us is the same value that we just saw before, except now it's using the custom HLSL. So this is really cool because now we can start manipulating the data with the actual inputs that we have. However, I did the same thing that I did before, where I have these new inputs and I need to make sure that they're set properly. So if I go to System Overview, go to Right to Grid, from here, I can set the radius scale to 1, and then make sure that location and sizes is actually hooked up to locations and sizes. So if we go back to the Right to Grid, we can go ahead and start getting our data from locations and sizes. So to do this, there's a really handy way to take a look and kind of get a little bit of a cheat code on how to write code in here. So if you right click on any of these inputs, you can go to Data Interface Function HLSL, and then you can say copy one of these to the clipboard. So what we want is the length of the array to start with. So we'll go ahead and we'll copy the length of the array, and we'll paste into the custom HLSL. And this will give us in location and sizes, that's the name of this, dot length, and then it'll say out int value of outnum. This will actually complain, and this is because the copied code is actually just telling you that this is an out value, so it means that this is going to be changed, and it's requiring that it's an int. So what you need to do is copy the int outnum here, and then delete out and int, and then paste int outnum at the top. Add a semicolon to the end, and now what you'll get is the length. And you can prove that the length is working, same way that we're proving before. We'll just go ahead and change this to be outnum, and now you can see, bam, our stuff in here is now showing. That's proving that the length is actually coming through and there is more than 0 in the array. Since we're gonna just actually start needing data, we're gonna go ahead and hit play. From here, we're gonna have to make a for loop. So we'll do for, or open close parentheses, then open and close brackets. And then the for loop is gonna be int index equals 0, semicolon, index less than or equal to the out num, and then semicolon again, out or index plus plus. And this is just a simple for loop iterating through whatever we're going to iterate through. So in this case, we're going to use the in location and sizes, and we're going to do the same thing we did before, where we right click and we do data interface, we say get. We'll paste the get in here. And when we do this, our get value will be the same type of issue that we had before. So we have to copy this index. And in this case, since we already have an index value, we can go ahead and replace this whole section with our index value. And then this one, we'll copy the float4 out value, and we'll paste it here, and then remove out. And this should compile. So if I hit apply scratch, it's actually not going to compile because we forgot to remove this float4. Now this time should actually compile. Cool. What we can do now is we can kind of test to see if the values are there that we expect. So if we go into the for loop here and we say return, semicolon, out RGB A equals out underscore value dot Y. And it's actually wrong. So our Y value is negative. So let's just test the Z value just in case. So Z is positive. So we do have data there. So that's really good for us. That means that the data is actually coming through for each of these array elements. And that's awesome because now we can actually start doing things like distance checks. So to calculate distance, we have our location value and we have our grid location. We'll go ahead and we'll make a const value. So this is going to be a value that can't change after we set it. And then we'll say const float distance equals length. And then we'll put our out value. So this is our current location in the array. So this out value minus the in grid location. Then we'll put a semicolon. The first thing we'll need at the top is a float4, and this will be our new grid value. And we'll set this to 0. Then from here, we'll go ahead and we'll adjust this grid value per iteration of this for loop. So we'll go ahead and say if distance is less than the out value, and our out value.w, which if you remember, out value.w is our radius right here. And then we'll multiply by our in radius scale. So if this is within the range of our in radius scale, we can set it to 1. So the idea is that this new grid value, we can say it's 1 now if it's within the distance. And then the last thing we'll do is we'll take this new grid value down at the bottom and we'll set it to our out RGBA. So now when I hit apply, you'll see we get something a little different, but it's not quite calibrated yet, but it is there. So if we go to our system overview, we can say right to grid, and then we can scale up our render target, you'll see, oh, we start seeing some spheres. We can also scale up the radius a little bit too, so that it's a little bit more apparent. And in this case, for the sake of this tutorial, I know that the value is 6, which lines up pretty well to the spheres. So now we see some spheres showing up. But you'll notice that they're all pretty, the spheres are pretty hard, like they don't have a nice fall off to it. And that's because we need to actually make the fall off. So if we go back to right to grid, we can create a fall off. We'll say const float fall off equals, and this is where we have a 1 minus. So we're going to flip our current distance divided by our radius in scale. So our current distance divided by this value here. So I'll copy this. We'll throw that in here. And this will flip essentially this value right now. So if I hit new grid value equals fall off, you'll see if I hit apply. Oh, I forgot a semicolon at the end. Then if I hit apply, you'll see now we have soft circles. But now you'll notice that they're kind of overlapping with each other. They're not doing nice additive process. So they're just layering, which is, you know, if you want to do that, that's totally fine. However, in this case, I want to make sure that they add on top of each other. So instead of just telling it to be fall off, we need to say new grid value equals new grid value plus fall off. And now all these values will add on top of each other. And just like that, we have our grid 2D system. So now we have all of our stuff with adjustable parameters able to kind of be used in a material based on all these positions. And you can kind of see that this is something that you can totally tweak. You'll notice if in here that there's no kind of like blending between things. If we wanted these to actually blend a little bit per frame, all we'll have to do is just get the current stack context. So if I type in RGBA as an input, send this in, and we'll call this, remember anything that we bring in here needs to be an in value. So we say in RGBA. Then from here, we can say apply. And something really interesting about these stack contexts is you have to change in their parameters. If you go to stack context sensitive and click on RGBA, you'll see this default mode is fail if previously not set. You can go ahead and set this to value instead. In our case, we don't really want it to fail, and it's fine that it's 0 by default. So now that we have our in RGBA value, we can take this and we can lerp it with our existing value. So we also need the delta time. So we'll take delta time. And same thing here, if we take in any input value, we have to make sure it's a different name. We'll go ahead and say the out RGBA equals, instead of new grid value, we'll say lerp in RGBA with our new grid value in delta time times 5, just to speed it up. You can see now that they're actually blending between the frames. So you get this nice like fall off between it, which allows you to do some really interesting effects. You'll notice that the performance for this, for the actual Niagara system is pretty negligible. It's around 0.02 milliseconds. Most of the performance overhead right now is going to be from this location manager sending the data. So this should be able to handle hundreds of nodes or hundreds of things on it without any issues. So you'll notice that there is one last issue to kind of fix, and that is this flashbang that happens. And that's because this initialized simulation stage needs to be set to an execute behavior of on simulation reset instead. That fixes that issue, and I forgot about that while we were making the initialize. That's it. But yeah, I hope this is useful for anybody who is trying to do something similar with whatever system that you're doing before, and this should hopefully run you through the basics of getting this set up. If you like what you see and all this stuff and you want to stay tuned with that, definitely follow me on your favorite social medias, subscribe to me on the YouTubes, and then also check out Mix Universe if you can, if you want to see what this was made for in the first place. Definitely check it out, and if you play it, let me know how it is, and yeah, have a good day.